Hello and welcome. My name is Richard Taverner and I'm your host of Any Further Questions. This is the third in our series of special episodes where I sit down with Chris Lintott, our current Gresham Professor of Astronomy, following each of his 6 lectures to ask him all the questions from our audience that we didn't have time to get to. This time he'll be answering questions from his lecture Oumuamua, our First Interstellar Visitor, which he gave on the 24th of January and is now available to watch on our YouTube channel. So it's probably a good idea to go and watch that first before listening to us. All episodes of our Any Further Questions are available to listen to on Spotify and Apple Podcasts, so please do go and check them out. Now, Chris, hi, welcome. How are you?
I'm good, thank you. It's nice to be here. It doesn't feel like a few weeks ago that we gave the lecture. I've been thinking about and talking about Oumuamua ever since, actually. So it's nice to be here.
Good. Can I just mention before we start that we had yet another question on Pluto following this lecture. So can I please refer everyone listening to this to go and listen to some previous lectures of Chris's and podcasts where we answer that question extensively and talk about Pluto.
It's still not a planet. I'm going to keep mentioning it. I don't know how I'm going to... The next lecture's on radio astronomy. I don't know how I'm going to work in a jive
You're
at
bound
Pluto,
to get some more questions on that.
I'll get that in somehow.
So for the benefit of our listeners and for a bit of context, can I first start by asking you to give us a bit of background on the main subject of the lecture, which is Oumuamua. What is it and what does the name mean?
Well, it's the most fascinating object we've found in years. It arrived from beyond the solar system in 2017, in October, and it was only found after it shot past the sun and started slingshotting out into deep space. So we found it after its encounter with the inner solar system. It's the first time we've seen a macroscopic, a large object. Maybe the thing was maybe 400 meters long and maybe 40 meters across. It's the first time we've seen a large object from beyond the solar system and caught it as it passed by. It's a strange world. We expected it to be objects like this to be like comets. There was no sign of a cometary activity. It had a strange shape, maybe a cigar shape, maybe a pancake shape, but certainly not round like you'd think of normal bodies in space. And most intriguingly, it sped up as it was leaving the solar system. So it fired its engines, and to some people, that showed alien intelligence shooting it off into space. I don't think that's likely, but it attracted attention. The name is Hawaiian. It comes from the people who discovered it, who used the Pan-STARRS telescope on the island of Maui. And so in Hawaiian, repeating a phrase emphasizes it. So mua is far away, so Oumuamua is really far away, and U is a scout, somebody who goes and scouts the land. So Oumuamua is a scout from really, really far away.
Thank you for all the questions sent in following Chris's lecture. The first question I've got is, why do you think the shape of Oumuamua is so unusual?
Well, I think the first thing we have to talk about is whether it was unusual. It was certainly surprising, I think. If you think of large things in the solar system, planets, even Pluto, the moons of the planets, larger asteroids, they're round. And they're round because gravity pulls them together. If you get to smaller objects, like the asteroids, for example, many of them are a bit more irregular. They're sort of potato-shaped. Or in the case of Comet Churyumov-Gerasimenko, the Rosetta spacecraft explored, it's more or less like a rubber duck, but it's two roundish things stuck together. And we see this sort of pattern throughout the solar system. So the fact that Oumuamua seems to be elongated, as I said, either thin and long like a cigar or a pen, or flat and thin like a pancake, flipping through the cosmos, is unusual compared to other asteroids. The truth, though, is that we haven't studied many asteroids that are a few hundred meters across in such detail. So it may be that there are a few other Oumuamua-like things in our solar system. Or another possibility is it does look, if you look at some of the artists' illustrations of these things, and in the lecture I had great fun showing people the best image we had of it, which is a dot, and then the beautiful artists' impressions of what this thing might look like that people have conjured up. It's quite easy to imagine it as a fragment of something. So it may be something you can imagine in a distant solar system, a collision between two larger bodies, and this fragment spun off into space. So maybe it's like a shard of something larger. It added to the general sense of intrigue about the thing that it didn't look like the asteroids that we've visited so far in our solar system.
Well, that leads into our next question quite nicely. Could it have been a remnant of rocky planet ejected as part of supernova, as the energy release would rip a planet in outer orbits like Pluto apart?
Yes, it's a good question, though. Pluto, of course, is a dwarf planet rather than a normal planet. So supernovae happen around very large stars, very massive stars, when they come to the end of their life. The sun has a sort of more gentle end to its life in store. And it's certainly true that as stars lose mass leading up to a supernova and then in the explosion itself, it's bad news for planetary systems, so we expect disruption. We do see sometimes a supernova will produce a neutron star, a dense remnant. Sometimes they produce black holes. Less massive stars produce these dense remnants known as neutron stars. And they can be pulsars, which we'll talk more about in the next lecture. But we do see planetary systems around those. So either planets can survive a supernova, or maybe they reform. In either case, towards a star's death, we think there is a pulse of interstellar objects, like for example, the stuff in the Kuiper belt out near Pluto, as the sun loses mass, will drift off into the galaxy. But that's outnumbered by what we think is the main scattering event, which is early in a star's history when planets are moving around in the disk where things are still forming. We lose most of the interstellar objects at that point. So star's death is important, but it's not as swamped as the early ones. And so given that we've only seen two of these things, it's a guess, but we think both of them will have come from that first phase of scattering.
Could Oumuamua acceleration be caused by various planetary gravitational assists while passing through the solar system?
Yeah, I got a question about this, or like this, from a very well-informed member of the audience who came up to me after the lecture as well. So that's you, hello. So the trajectory brought it in, it slingshotted around the sun, and it certainly sped up because of that slingshot. We can measure the difference in speed between what it's doing now and what it was doing before the encounter with the sun. And you can make the same calculation for the other planets as well. It didn't get very close to any of the other planets. It didn't even come very close to Earth. And so they were basically negligible. There's not much effect from Jupiter and Saturn and all the rest. And what was seen as it was receding was we've got this new accelerated velocity following our encounter with the sun. That's good. We can calculate that. And then it should be slowing down because of the sun's pull, and it's not slowing down enough. And that happens over the course of several weeks. So whatever's causing it is an ongoing force. It's not just an impulse or an encounter. There's something that's happening over a long period of time.
What data or observations were used or made to determine this object came from outside the solar system?
So this turns out to be the easy bit. Once you find it, there's two pieces of information we have. So one of the things I was keen to talk about in the lecture was that we only see a dot moving through space. How on earth can we deduce anything about a dot moving through space? Well, you can tell a lot. And two of the things you can tell pretty quickly are where it came from by tracing back the path. And we can see that unusually it came from out of the plane of the solar system. So if you think all the planets are in the plane, that's why they stick mostly to the zodiac in the sky. Oumuamua came from above that. So that's not completely without precedent. Comets sometimes do that, but it's a sign there's something unusual. The other thing you can measure really quickly is how fast it's moving. And it's going fast enough that we know it can't have been bound to the sun before. In other words, if you take something... The other possibility is that you take something out in the Oort cloud, which is the supposed reservoir of comets that's a third of the way to the nearest star. Sometimes those things encounter each other and one of them is thrown in towards the inner solar system. But they come in slowly. It's not a lot of energy, and they sort of fall in like starting to fall down a gentle slope before they accelerate in the inner solar system. We can see that Oumuamua came in fast. And that's the distinguishing thing that makes it an interstellar object.
So could it come back?
Could it come back? It almost certainly, not only will it not come back, it's probably not going to encounter another star. So it's moving fast enough. It's not what we call bound, so the sun's gravity was insufficient to hang on to it. And so, no, it's unless there are aliens on board and they're doing a U-turn, it's definitely not coming back. If it comes back, I'll be prepared to admit that it's an alien spacecraft for sure.
You gave the analogy in the lecture about the crispy shell like a magnum.
Yes.
Does the crispy shell model apply to most of the many millions of undetected interstellar visitors?
Well, it's a good question. So this was an explanation for why it didn't behave like a comet. So I think there are three possibilities. One is that it's not a comet at all, that it's a rocky body like an asteroid. But we have good reasons for believing most of these things will be comets. The second interstellar visitor, Borisov, really was a comet, grew a tail and did all the comety things that you'd expect. And also, if you think about it, they have a small body in the outer solar system. It requires much less effort to get away from the sun than something down here in the gravity well in the inner solar system. And so we really do expect most of these things to be icy. So that possibility seems unlikely. Second possibility is that it is a normal comet, but the conditions weren't right for it to develop an atmosphere and a tail, or we weren't good enough at looking. It's possible, but we looked really hard. Third possibility is there's some change that's happened to it while it's been travelling. And if we believe, as I think we do, that Oumuamua has been out amongst the stars for hundreds of millions or perhaps even billions of years. Actually, I think to be more precise, using the work I mentioned in the lecture by my PhD student Matthew Hawkins, who's now put the paper online, there's no evidence that it's young. So on average, most of these things should be out there for hundreds of millions or billions of years. Then you take this block of ice and it's exposed to cosmic rays, high-energy particles in the galaxy that maybe can excite the water on the outside and create this crispy shell with the ice in the middle. If that model's right, then that should happen to the vast majority of interstellar objects. But now we've got a problem because we've seen two and one of them behave perfectly like a comet. And so maybe Borisov was larger. Maybe Borisov was young. There's no evidence either way, really. What we really need to do is find some more of these. I'll be a lot happier when we can have these conversations with 3 or 4 or 5 or 10 of these things.
Why is it red? Why would something from outside the solar system made of ice be red?
I'm glad you asked this because I don't think I explained this very well in the lecture. It was one of the first things I talked about because, again, simple measurements. You've got a dot, you can measure its colour. So things in the outer solar system tend to be red. So if you think of those images of Pluto from New Horizons or even Pluto's moon, they have these red deposits. And they're often chemicals called tholins. And they're the result of processing of nitrogen, ice, carbon dioxide, water by exposure to quite a hostile environment. So I think red here means old. It's an old surface that's been processed. And so the fact that it's that sort of red colour tells us that it's an object that either lived a long time in the outer solar system of wherever it's from, or it has travelled between the stars and been processed. So when you form fresh new ice, it's bright white, and then it gets chemically altered over time. So we can use the colour of things in the outer solar system. It tells us what they're made of, but we can also use it to sort of give us a history or a hint at the history of these objects.
Please could you explain more about how melting ice would give an acceleration effect? If Oumuamua was tumbling, how does melting cause acceleration?
Now, this is a really good question. So
this was actually the most liked question.
This is really smart. So this puts together two sets of things that I said. So one of them is that I said, look, if it's a comet, we can expect acceleration. And the reason for that is we know when you look at a comet, when we've flown up close to them, particularly when they're close to the sun, they lose a lot of material. The ice sublimates, it turns into gas, but it doesn't do so evenly. It's not like an ice cube melting on a hot day. You get jets of material where fresh ice has been exposed and heated by the sun. So you do see these jets of material shooting away from Rosetta. Now, one of the unusual things about Oumuamua is that it's tumbling. So not just turning, not just orbiting, but chaotically tumbling. Something that some people have said, well, look, this must be a chaotic origin. It's one of the reasons why we believe it maybe started in a collision of bodies. But if you're tumbling, even if you have a jet and then you have this thing tumbling around, you can imagine it'll be like a sprinkler going all over the place. You don't get a consistent push. So this is a really good question. So you need to claim that the jets are going to be short-lived. When they form, they're going to give a brief burst and then shut off. And then they always face the sun because it's as it tumbles, it's whichever side is facing the sun. So don't think of it as one jet. The idea isn't that there's one jet that's there for many days. It's that on average, it's the bits facing the sun that develop these short-lived jets. Now, again, we've only seen this thing as a dot and we didn't see any sign of cometary activity. So I've no idea if that's the right model, but you do have to tweak that model and to account for the tumbling. So If you were somebody who believed, and there are plenty of these people who believe Oumuamua was exotic, something like a hydrogen iceberg or something like that, that would be an argument in your favour, I think, was that at this point I'm sort of custom designing jets that turn on and off at will just to explain what's seen.
And if you had to put a percentage on the likelihood Oumuamua has a natural origin, what is your best guess? Is there even a tiny chance it may have an artificial origin?
So this is an interesting question. So it's very difficult to put a percentage on that because I don't know how to test the hypothesis that Oumuamua is alien. It's an idea. We should consider it. But I think one way to answer the question is to think about how many objects we would have to find from what we know of the... So I've done some work, again, with my PhD student Matthew, to look at what the properties of the interstellar object population should be, based on what we know about how asteroids and comets form and where in the and the whole history of star formation in the Milky Way. And we think that if you get the next 50 interstellar objects, which we're likely to do in the next, maybe even the next 5 years, something like that, with the new telescope I mentioned at the end, the Vera Rubin Observatory. We got the next 50, there might be one that has properties similar to Oumuamua. In all the different ways it's unusual. So it's a 1 in 50 unusual chance. So the question is, for you, whoever asked the question, if I tell you that something is only 1 in 50 natural, is that enough for you to go, well, it must be aliens? Or is 1 in 50 sort of the kind of thing that happens every day? Now, Avi Loeb, who's the main proponent of the alien hypothesis, has a different number from his ideas. He says there's a 1 trillion to 1 chance that Oumuamua is natural. Because he does the same thing of adding up all the ways it's unusual. And he comes up with I come up with 50 to 1. He comes up with 1 trillion to 1. And so for him, he says, look, at this point, aliens is the sensible answer. And I think that's right. I think if you've got 1 trillion to 1 chance that it's natural, and you've only seen 2 of these things. Unfortunately, Avi's wrong about the 1 trillion to 1, right? We've actually done the work, and Matthew spent 1.5 years of his life doing the calculation properly. So I think 50 to 1 is not enough for me to take aliens, but that doesn't mean it's not an interesting thing.
What kind of research is this fueling, and what has it done for the scientific community discovering Oumuamua?
I think it's kicked a whole lot of people into action, which is fun in a few different ways. So let's start with there's a whole bunch of people trying to understand Oumuamua still, trying to argue about what it might be and what sorts of objects there might be out there for us to find. A lot of the more speculative ideas, like the hydrogen icebergs and things forming directly in star-forming regions, come from that. So that's been great fun. I think there's a group of us for whom the great realization for me, which I talked about at the end of the lecture, is that we are citizens of the galaxy, that our solar system is connected directly to stuff that comes from other stars in the galaxy. And it turns out, once you dig into the subject, it's not just from our neighbouring stars. These things should be arriving from all over. And so to understand them, we need to bring together 2 very different branches of the science. We need to take the people who study the small bodies of the solar system, the comets and the asteroids, and the people who write down equations that govern 13 billion years of galactic history. And those groups don't talk to each other. And so there's a group of us now who sit in the middle, or who are in one camp or the other, who are actually working together to try and predict what we're going to see. I think a third thing that it did was convince us that we should have found these things before. We found 2. There's probably lots more out there. And it's not utterly clear that telescopes like Pan-STARRS, though they do a good job, are being efficient at finding these objects. They're faint, they're fast-moving, and frankly, they're not what we were looking for until now. We were looking for near-Earth asteroids, things that might threaten the Earth. We were looking for distant Kuiper belt objects, which are slow-moving. So no one's done a systematic search of these, and so people are starting to think about new ways to find these things, particularly with new telescopes. And more generally, I think the alien speculation has, in one sense, been useful in that I think it's broadened the ways that people think about trying to find evidence of alien life. And so we've always thought about SETI as a distant thing, about listening for signals or detecting the pulses of light from alien spacecraft. But I think there are now people taking seriously, and funding to some extent, work to say, okay, if there was an alien spacecraft in the solar system, would we find it? It's a slightly unsettling question to think that right now the answer is probably no, because of this problem that we're really only looking for things that we expect. And so there is a groundswell of interest in looking for unusual things in the solar system, partly because we'll find new classes of asteroid and new classes of object that tell us about the history of the solar system, but maybe 5% because it's fun to think that we might see an alien spacecraft. If you found something, for example, in orbit above the solar system, so you've got the plane of the solar system, you found something on an orbit that swung round the sun over the north and south poles of the sun, and maybe once every 100 years swung past the Earth, that would be hard to explain with a natural model of how you got something there. And B, that's the kind of orbit you'd put a craft that was just keeping an eye on us in. So I think if you found that, I'm not saying it would be aliens, but I think you'd take that quite seriously and try and explain what was there. So that's been fun too. I think that's stimulated people to do that sort of work.
Is it now lost to the JWST telescope as well?
Yes, no telescope on Earth can see it. James Webb JWST, which of course isn't on Earth, none of our telescopes can see it. It was lost to the big ground-based telescopes. Actually had the best chance here because here with faint objects, particularly in the optical, JWST is in the infrared, size of mirror counts. And so it's the 8-meter telescopes, the very large telescope, for example, that tracked it longest. But no, it's lost. And that's why I got some questions after the lecture about why we can't send a probe after it, why we can't chase it down. And there is a group who have been publishing calculations about how fast you'd have to send a spacecraft to catch it up. But the problem isn't catching up, the problem is knowing where it is. We only saw it for a couple of months, and so the error on the trajectory is quite large. And so I think even if you could travel at half the speed of light or something, I don't think you'd be able to find it right now.
So from analysing these comets and asteroids, are the scientists looking for biological indicators? And if so, could we trace their source?
Yeah, this is a really good question. So we can broaden out from Oumuamua to studying icy things altogether. And certainly people are looking for complex chemistry. So one of the reasons we sent the Rosetta probe to a comet was to sniff out what chemistry was there. And people were looking for things like amino acids. And while we didn't get that complicated, they did find some reasonably advanced organic chemistry. And organic here means having carbon in, but it's the complex chemistry that heads towards life. And so, yes, comets do seem to have this rich source of chemicals, and we know that the Earth was bombarded by many, many, many billions of comets and asteroids early on, and so there's this nice idea that maybe that's where the building blocks from life came from. I think it's a fascinating idea. What we'd ideally like is if each molecule that life used had a label saying where it was from. That would be really helpful. People have looked for such labels, so quite often we can use what's called deuteration, where you replace the hydrogen in a molecule with deuterium, heavy hydrogen, to make things like heavy water and so on. And the ratio of deuterium to normal hydrogen in a particular molecule is a signature of where it's come from. And so one of the great games that astrobiologists and astrochemists have been playing is to look at the deuterium fraction in the Earth's oceans and try and find things in the cosmos that match. Because then you could say, okay, that's the source of the Earth's water. And the results from comets are frustratingly ambiguous, but they're basically all over the place. We haven't yet found a large number of bodies where the deuterium fraction matches. So it's not utterly clear that the story that's often told that our water comes from comets is actually true. Of course, we could be more speculative. If we have biological molecules, maybe even very complex biological molecules on interstellar objects being carried between the stars, then of course you could seed, just as I was talking about them as seeding planet formation, you could end up seeding your solar system with the building blocks of life. I think that's tempting, but the mass involved, you're always going to have much more material locally than you are from the interstellar objects. Plus, they're going to disappear from the solar system early on, so maybe before life got going. So while it's tempting to think of hitchhiking bacteria, I think it's more about, that's a story about comets in our solar system rather than these interstellar objects.
So we saw Oumuamua as it passed and we observed it, and we've covered the fact that it would be very difficult to see where it is going or catch up with it. What about plotting where it came from? Are we able to do that? Have we done that?
Yeah, so we can do that a little. So we can obviously just trace the thing back. And when you do that, you find it doesn't point directly to any of the very nearby stars. So there was this idea that maybe this would be a local phenomenon. You get visited by your neighbours, but not by relatives from a long way away. So that doesn't quite work. And then you have this problem that we only observed it for a little bit of time. So our ability to trace its precise path is limited. What we can do is look at how it moved in the galaxy. So we do have a good idea of what its velocity was before it dropped in. And it's interesting what we've shown, this is my group again, have shown that it matches the way that a group of stars called the Pleiades moving group move. Now, maybe some people have heard of the Pleiades. It's a bright cluster in Taurus. I saw it last night. Beautiful sight in the winter sky. And they're all young stars, but they're part of a much larger association of stars that move through the galaxy together. Not because they were born together, but because they've had the same kind of encounters with the galaxy's spiral arms, and they end up in a sort of pattern. Yeah. Same way, I don't know, like you end up walking through a busy tube station, you end up in sync with a set of people. It's that sort of thing going on. And Oumuamua is moving, or was moving before it encountered the sun, like that. So it must have come from one of those stars, but there are hundreds of thousands of such stars. And there's no reason to believe it came from the Pleiades, which are nearby, versus something that's on the other side of the galaxy right now. One nice thing, though, is that because of that match, we can be pretty sure that it didn't encounter a star before. So now it's been past the sun. We've scrambled its velocity, right? Its velocity now tells you about its encounter with the sun, not its behaviour in the galaxy. And so we can be pretty sure that it was a first-time visitor. This was its first encounter with a star since it left its home system, presumably billions of years ago.
We had 2 questions on Bennu. Can you just
which I started the lecture with, yeah.
Talk about a bit about Bennu?
Bennu has this reputation. It's the most threatening asteroid we know of. It's the large asteroid with the best chance of colliding with us. I think it's a 1 in 2,500 chance sometime in the next century, in the 22nd century. So this is a real threat, and there's actually nothing we can do about it right now, because whether it will collide or not depends on its behaviour towards the end of this century when it comes very close to the Earth. Now, it won't hit us then, but the Earth's gravity and the Moon's gravity will change its orbit, and it's hard to calculate exactly what will happen. So, for all sorts of reasons, studying Bennu is important, and we just had the OSIRIS-REx probe that visited, encountered it really. It tried to touch down with a probe, but it turns out Bennu's basically a rubble pile. And so it was like plunging your hand into a sandpit at speed. But it has brought material back to Earth. And so now we have samples of Bennu back here. We have them here in London, but around the world as well. And the idea is that because it's a small object, it's likely a relic of the very early days of the solar system. So we'll learn a bit about how the solar system was built up. We'll learn a bit about how these things move through the solar system. And we'll know more about it for a century's time if we need to intervene if it's going to hit us.
Well, our first of our 2 questions was, why would we want to deflect Bennu if it's just a pile of fragments?
Well, it's quite a large pile of fragments.
Could it do some damage?
Yeah, I think it's an interesting case that you'd have to, obviously a solid body hitting the upper atmosphere, more of it's going to hit the ground than if you have a large pile of fragments, a pile of rubble, which will boil up. But I think you'd need to do some serious, and I imagine people are going to do some serious supercomputer modelling to work that out. Remember, though, we don't actually know what's in the middle. So somebody will need to do some work to work out the density and see whether it could be a core surrounded by rubble. So I don't think we get off scot-free just because it wasn't as solid as we expected.
Well, that ties into our second question, the chemical composition of Bennu. Do we know much about that?
We know a bit from the ground.
Is it typical of all asteroids?
It's from, I'm trying to remember which, but it's from one of the asteroid families. So asteroids fall into 3 or 4 big families. And Bennu is pretty typical of its class. So hopefully by learning about Bennu, which the first one we've gone and got lots of material back from, we'll know more about many of the asteroids from its families. It's part of a broader suite of missions. The Japanese have been to Ryugu, which is a different asteroid, and brought bits of that, just a few grams of that back, but still that's back on ground as well. And so we're beginning to build up a picture of these things in the laboratory. Of course, it seems a bit silly. Why don't you've got space probes? Why do you need to bring bits back? But But of course, you can do many more tests in the laboratory than you can do with a miniaturized set of instruments on board a spacecraft. And I think one aspect of the mission to Bennu that I really like is that I think 60% of the stuff they brought back won't be touched right now, because the assumption is that in the future there'll be new techniques developed, there'll be new machinery developed, so you'll want to save some pristine material back for whatever we can find out in 50 years' time, just as people are still working on the Apollo samples now that the astronauts brought back.
That was all the questions we had online. There's a final question from me. I wanted to ask, when the next Oumuamua comes, how, in your opinion, can we prepare ourselves with technology in order to get a better idea, maybe a sample of it? Is that possible?
Yeah, in the short term, we're all standing by with telescopes, essentially. So we've done the bureaucracy. And I know that sounds ridiculous, but we've already got proposals into many telescopes around the world that says, if we see one of these things, we're going to interrupt what you're doing. And we've got permission to do that. So I think we'll get better observations this time. I think you really see with Oumuamua that we didn't get spectra of it. If we'd seen it earlier, we might be able to see its spectrum, not just a point of light.
Sorry, what year was it observed?
2017. But because we'd seen it after it had gone through the sun, it was fainter.
Right.
And so it was too faint for even the very largest telescopes to do that. If we'd seen it coming in, maybe in early 2017, we would have been able to do more. So I think we're more ready than we were. In terms of chasing it, we've got an exciting European and Japanese mission called Comet Interceptor, which is going to launch in, I think, 2028. And Comet Interceptor is a brilliant idea. So the problem with sending probes to comets is you have to have found the comet before you launch the probe. And so far that's meant we've only visited objects where they've already been through the inner solar system. So they've already been processed by the sun. What we'd like is to find a comet on its first journey in, or even better, in my opinion, an interstellar object. And so Comet Interceptor launches, it's got 3 spacecraft, and then they just sit and they wait. And you can wait for up to 10 years, but at some point in that 10 years, you press a button and you hair off to a new comet. So my hope is that Comet Interceptor will go to an interstellar object. Hopefully not the next one, because we're hoping to discover many more before then, but that will be a chance to, probably not to bring a sample back, but to go and take a close look and hopefully travel with it as it passes around the sun, so we can see if there are jets, if there is activity, we can see this sort of behavior unfolding. So that will be very exciting. I think what we need to do next is work out the odds of seeing an interstellar object at a velocity that Comet Interceptor can get to. So we're sort of playing this interstellar, or intra-solar system at least, game of tag, and we need to work out if we would be able to catch these things. If we are, then we can make a case to say, never mind your comets, wait for an interstellar object.
And 2028 isn't really that far away.
It's not, and we'll have the Vera Rubin Observatory, which is this big survey telescope in Chile that we think will find, I don't know, it could be 2, it could be 200, but maybe 10 a year of these things is a reasonably optimistic amount. So then we'll have a selection to choose from by then as well.
Thank you very much for joining me today, Chris, and thank you at home for listening. By the time this episode's released, Chris will be preparing for his 4th lecture in his series, Pulsars, Microwave Ovens and the Radio Sky. Can you tell us a bit about it?
Well, I should be preparing for it already, so I'll try. Yeah, I think one of the exciting thing about this for me is that we're going beyond the opticals. So the story of 20th century astronomy is learning to look at the sky in wavelengths that our eyes can't see, and radio astronomy is central to that. And I think there's a set of wonderful stories from the pioneers of radio astronomy, like Grote Reber, who built the first steerable radio telescope and then fought his mother, who wanted to hang her washing on it, to Jocelyn Bell Burnell, whose story discovering pulsars as a PhD student in Cambridge is actually quite deep and profound, to a more recent story involving a microwave oven that I'll save for the lecture. But let's just say microwave ovens emit radio waves when perhaps you don't want them to. And then the universe that those discoveries have revealed contains black holes and colliding neutron stars that produce the gold in your jewelry, and the very distant universe as well. And so I think this should be a completely new way to look at the universe, and I'm looking forward to telling people about it.
Chris, thank you very much.
Thank you.